All right, it should be recording. All right, welcome to the worksheet review. This is going to be a part one of two videos, ideally, if things work out, going over the practice exam as well as this worksheet. So let's go ahead and dive into this. So when we're getting to equilibrium, this is going to be a very, very big concept because you'll be seeing it in a little bit of test one, I'm pretty sure. Especially in test two and test three, they're very big on equilibrium. Even in organic chemistry, if you're going to be taking that, there's a big equilibrium just concept as a whole. So if you're going to be taking higher level science classes, especially in chemistry, this will be a very big concept because you'll also see it in biochem. Um, the main concept is whatever your equilibrium constant is pretty much always going to be product over reactant. Okay, that's all it consists of. And if you have multiple products, it's going to be your like product one, product two. There's sum of all of your products and your reactants, reactant one, reactant two. So it can be broken down into many things. All right. Now, for KP and KC in particular, they are kind of conversions of each other because KP is more related to the equilibrium constant of gases. And I like to think of P as in like pressure because, from Pivner from semester one. Yeah. So KP is your equilibrium constant of gases equals your Kc times some kind of conversion constant. Because remember, your Kc, you multiply it by something in order to translate it basically to your Kp or your equilibrium of your gas. And that conversion constant will be RT. And that product will have an exponent on your delta N. Now, your delta N is very crucial. Sometimes you'll have questions that'll ask you, like specifically, what is the N delta N for the reaction, or which one would have I would know, I don't know, like the highest KP, and you're looking for like the highest delta N, stuff along that line. But your delta N is just counting the moles. So delta N will be your moles of gas in your products minus your moles of gas in your reactants. All right. So if your product has 2 moles of gas and your reactants has 3 moles, that would be 2 minus 3. You have an exponent of -1. That's your delta N. Okay. Now, drawing out our equation as a whole, Kp equals Kc times RT delta N. Well, you're given a temperature, 25 degrees Celsius. And remember, you have to convert it to Kelvin because chemistry, we like to use Kelvin. It's very uniform throughout. 25 degrees Celsius, you just add 273. That's going to be 298 Kelvin. R, that's going to be a constant. That's going to be 0.0821, your gas constant. And you solve for N, which is -1. And now you just have two variables left. If you look up here, you're given one of them, right? So if you're given this, you only have one variable left and you just multiply it out. So if you're given this, it translates to, what is it? Kp is 2.2 times 10 to the 12 equals Kc times 0.0821 times 298 Kelvin to the -1 power. Now the entire product and the exponent will multiply up to 0.04087. So you just divide that over. So divided by 0.04087 cancels out. Do the same thing on the product side. Divided by 0.04087. Your Kc ends up being 5.4 times 10 to the 13th. And remember, the equilibrium constant is a ratio. So there's not really a unit for it because it's a ratio, it's a constant. We're going for number 2. Consider the following reaction. You'll have hydrosulfuric acid, you have decomposition reaction. All right. They give you your Kc constant. All right. Now, are the reactants or products favored in the equilibrium? If you remember Kc, or your equilibrium constants as a whole, is your product over reactant. So if you have very high product and very low reactant, your Kc constant will be very high. And you'll see this in like strong acids, strong bases, because they dissociate completely. And if they dissociate completely, they produce the most amount of products. So product over reactants is going to be a very high ratio. Your Kc is going to be very high. Conversely, if you have a very low product ratio, very low, your R is very high, your Kc constant will be very, very small, because you have a very small number like 1 over a very big number like, I don't know, let's just do a random big number like 1600. All right, that's going to be a very, very small ratio. So Kc will be small. All right. And this means at equilibrium, the reactants will be favored. Okay. Because this constant, remember, is at equilibrium. So if at equilibrium, your product is very low compared to your reactants, well, at equilibrium, your reactants are going to be in much higher concentration. They will be favored. So in actuality, if you're looking at this equilibrium, the equilibrium arrows would look more like this. I don't know why I wrote 2 twice. Right? The equilibrium will shift to the reactant. Now, what if we change it up a little bit? What if we flipped it and then decrease or increase the coefficients? And for this one, we decreased it. All right. How does the reaction compare to the earlier part? Well, this brings in our reciprocal rule and our coefficient rule. All right. So if we reverse or just flip the reaction, we do the reciprocal rule. So if Kc is equal to our products over our reactants, well, in this equation, we flipped it. So our flipped version would be our reactants over our products relative to what we had initially. So if that was the case, then it would be 1 over our original Kc. And that's why we flip it in that reciprocal. Conversely, or not conversely, additionally, if we decrease those coefficients, we also decrease the order. So whatever we have, we decrease by a magnitude of, I think, a half. Yeah. We multiply it to the power of 1/2 inches to the bottom. There we go. So in this situation, our Kc constant will be our products over our reactants. H2, S2, and don't forget those coefficients become those exponents too. There you go again, H2S. That too becomes that exponent. Okay. Okay, cool. Now, that's our initial expression. And now we've not only flipped it, we also decreased it by half. So for the first part, we just flip these top and bottom. All right, so now our H2S is at the top, and our H2 and S2 are at the bottom. Not only that, our coefficients change. There's 1, 1/2, and 1. So our coefficients are 1, 1, 1/2. That's what it would look like. Yeah. And then in actuality, again, this was our initial one. And when we had that change right here, reciprocal, and then we had to the 1/2 power because we also decreased all the coefficients by 1/2. So this mixes both of them up. You'll probably see that on your test. So if you're given a K value of, I think it was given up here. Yeah. 1.7 times 10 to the negative 7, what is our new K value? So if our initial K value was 1.7 times 10 to the negative 7, well, remember, we flipped it, reciprocal rule, 1.7 times 10 to the negative 7. And then coefficient rule, we raise it to the power of whatever we multiplied everything by. We multiplied everything by 1/2, so we raise it to the 1/2 power. 1.7 times 10 to the negative 7, 1/2. All right. That should give us 2.4 times 10 to the 3. All right. Number 3, we will deal with ice boxes. It's a lot of fun. You'll see a lot of this in test 2 and test 3. It's a lot of fun. So look at our reaction. We have gaseous nitrogen and hydrogen, and we're making ammonia, right? So they're giving us initial concentrations of both reactants. And when equilibrium is reached, the pressure of NH3 is, or they give us the concentration of the product as well. Yeah. Calculate the Kp. So if our Kp is, remember, our K constant, products over reactant, we're looking for the concentration of ammonia, N2, H2. You don't actually add them. There we go. But remember, that's at equilibrium. Okay. So if it's at equilibrium, K is only at equilibrium. If it's not at equilibrium, we use the variable Q, which I don't think we deal with quite yet. But let's go ahead and add our exponents, 2 and 3 for ammonia and hydrogen respectively, 2, 3, the 1 power. So if our Kp value, Kp, I think we actually solved that down here. Getting ahead of myself. Yeah. Solve it down here. No. And that's gosh, we change it. This is my cat, by the way. He's getting in the way. Oh. They give, that's right, when equilibrium is reached. Okay, they give us the final concentration. So for our initial concentrations for the reactions are 0.866 atmospheres, 0.0496 atmospheres. And then our final product is 0.0310 atmospheres. All right, for given the situation, you can assume that there's no product left because we just put the 2 reactants in the whatever container we have. In this case, it's a flask. Okay. So now we have to do our minus, plus. This will be the case because we have no products in. We're going to shift to the right. We got to make some product. So what do we add by? Well, we know that in order to get this final product, we have to add 0.0310 atmospheres. Okay. Well, what do we subtract by here in our ice table? We use our molar ratio. So if 2x is added here and 2x is 0.0310, we have to subtract 3x from over here. Okay. 3x would be our 0.0465. Yeah, small ratio. Yeah, 0.0310. Divide that by 2 because that was 2x. So 0.0155. That's our x. Now, we multiply that by 3 because we need to get 3x. This molar ratio, basically multiplying by 3 halves. 0.0465. That's how we got that number. Okay. This one, we just subtract by x, and x is still 0.0155. You subtract that, atmospheres, 0.8505 atmospheres. Excuse me. 0.1 atmospheres. Pretty sure that's right. Yeah. Okay. Now we just rewrite the expression. K, oops, Kp equals our products over reactant. It's going to be NH3. I think that was to the second power. Yeah. H2 to the third power. Then our N2 to the first power. Let's get our final equilibrium concentration. It's going to be 0.0310 squared, 0.8505 to the 1 power, 0.0001 third power. Should be 3.8 times 10 to the 4. Yeah. Okay. Also, I don't want to waste time doing the calculations in a calculator and like punching them in. So I have like the calculations already like pre-written out. That's what I'm writing down. And you guys should have access to this worksheet as well.
Wait one sec.
All right. Number 4, consider the reaction. You have COF2, CF4 and CO2. KC for the reaction. Concentrations at equilibrium. So they give you the equilibrium stuff, concentrations. So the expression for Kc, remember Kc is products over reactants. Again, our products are going to be CO2 times CF4 over our reactants, which is just COF2. Then let's go ahead and put our coefficients there. It's going to be 1, 1, 1. Both of them are to the first power. 2 to the second power. And if they're already at equilibrium, well, they did the work for us. So if it's at equilibrium, our concentrations are, for CO2, is going to be 1.10 molarity, 0.118 molarity, and then 0.255 squared. That should just give you a really clean ratio of just 2. Yeah. I will say something very handy to know in the test. I'm pretty sure what you can do is if you're given a mixture of molarity and atmospheres, they're interchangeable. So if you had like 1.10, I don't know, atmospheres, and then 0.118 molarity, I'm pretty sure you can just use that normally. I'm pretty sure they're pretty interchangeable. Because last year, when I TA'd last year, I didn't really know the answer to that because I saw people do that and there was no real conversion between them. But I think on the test, when they just like left it as it is, where they interconverted, I think they got it right. So if you ever come across that, just leave them be as they are and just treat them the same. It's a pretty handy note. There's a chance you might not see that. So if that's the case, then don't worry about it. But if you do, good luck, and hopefully you remember what I just said. All right. So if we have our equilibrium constant of Kc, all right, now that we can work with. So if we're given new concentrations of stuff just added to a flask, more reactants, then we can solve for the final concentrations at equilibrium if we have the constant. So if we're just throwing reactant in 0.250 molarity, right? And it just goes inside a flask, so we can assume there's none of the product quite yet. What is our what are our equilibrium concentrations? So if we know that, okay, for every 2 moles of COF2 destroyed, you're creating 1 mole of CO2 and 1 mole of CF4, right? So if we just left in our icebox, okay, 0 plus X, 0 plus X. That's just going to be X. 0.250 minus 2 moles, because molar ratio, just ratio as a whole. And you might be thinking, all right, well, how do I know what's plus and what's minus? Well, for this situation, whenever you have something that's 0, all right, so if you have no reactant at all, or if you have no product at all, that's where you're going to add to. Because if you have no product at all and you throw some reactants in it, well, the only direction to go is to make product. So you're going to add molar ratio to your product side. I'm just going to do like a little, if you're only given product and somehow you just throw a product in, it's going to favor the reverse reaction. Because if there's no reactant, then there's only one direction to go. That's to the reactants. For this situation, really easy, no product. So we just go that way. Okay. Oh, that's what this question is asking. Okay. What direction does it go? Well, it goes to the forward reaction right here, because we have no product. That's the only direction to go. I guess that was simple enough. Okay. So if we have our relative concentrations, if we let the variables as it is, because remember, X is just a ratio and it's just the same variable used for our reactant and products. Well, let's put that in our Kc expression. So if remember, Kc, that equals 2, equals CO2, CF4, COF2 to the squared, or squared to the second power. All right. Well, now let's plug and chug our stuff. We have X. All right. And then for COF2, that was right here, 0.250 minus 2X to the second power. All right. Well, if you multiply these together, that's just X squared. If both of them are squared, well, we can just take the square root of both of them. Get rid of those exponents. Okay. Remember, okay. Maybe I'm going a little too fast. 2 equals X2. It's 2, that's our Kc, is our expression. 0.250 minus 2x2. Okay, so we take the square root of our Kc, take the square root of both sides, which is mathematically correct. All right, cancel out our squares. That means square root of 2 must equal x over 0.250 minus 2x. Okay, so that's what we have. Well, the square root of 2, that's 1.41. And now we just have our variables left. No exponents, nothing weird. So let's just multiply this over times 0.250 minus 2x. Well, that'll cancel out with the denominator, times 0.250 minus 2x. That's going to be 0.3525 minus 2.82x equals our original x. That numerator right here. So we add that over, 2.82x plus 2.82x. Remember, there's a 1 there. It's 1x. That's going to be 0.3525 equals 3.82x. And our x would thus be 0.0923 m. That's what our x is. However, most of the time, do not just write that in your E row. Because what if you had, for example, like this, 2x. You have to plug in that x into the 2. There's one more step. You got to multiply it in. So in actuality, this would be 0.250 minus product of 2 times 0.0923. That's what you would put there. Same thing with the x. Thankfully, it's just 1. You just leave it as it is. It's not multiplied by anything. It's multiplied by 1, 0.0923, 0.0923. Right. Part C. Okay. Same equation, same stuff. Our KC is still 2.00. Right. So if you put in all three, okay. So we're starting out 0.100 molarity, 0.2 molarity, 0.2 molarity. All right. Which way do we go? I write a note on this. Oh, yeah. So that's all we can fill out for now. And now we're looking, okay, in which direction, forward or reverse, does the reaction go? Well, if we're given non-equilibrium values at the very beginning, we can't really tell. Because if you didn't know the K beforehand, what if your K is really small, all right, and you actually want a lot of reactants? Or what if your K is actually really big and you just want a lot of product? You can't really tell. You know your molar ratio, this could be plus or minus 2x, like before, plus or minus 1x, plus or minus 1x. Well, we can tell that by using Q. Q is the relative amount or the relative ratio not at equilibrium. So you should go ahead and make that connection. K must be at equilibrium. The moment the reaction is not at equilibrium, you're looking at Q. The moment it is explicitly at equilibrium, you can use K. Make that distinction. So if Q equals our, remember, CO2, it's Q, we just do the same expression, just different non-equilibrium numbers. Okay, this Q is very related to K because they're the same equation. CF4, both to the first power, CO, excuse me, F into the second power. So if our initial concentrations were 0.2 molarity, 2 molarity, over 0.1 molarity, 2, that ratio is 4.00. All right. So if our K value equals 2.00 and our Q value equals 4.00, well, we have too much product. We have too much product. Because remember, it's a ratio of product to reactant. So if you have a higher Q, then you have too much product compared to reactants relative to what the reaction wants, which is at equilibrium. I know that's a very confusing sentence, but the more you think about it, I promise, the better you'll feel, hopefully, if you're starting to get it. If not, then, gosh, power to you. Because it's all, I think it all comes to practice. The more you see it, the better it is. I think that's it. So remember, if, Q, product over reactant, K is product over reactant. Well, if our ratio for Q is 4, we have a lot more product compared to reactant relative to K, because K is another ratio. So this was 2 product per 1 reactant. Our Q is 4 product per 1 reactant. Don't write this down. It's just to show you conceptually. Well, if you compare our products, there's a lot more product in the Q. So if it's not at equilibrium, it's using Q. And from what we can tell, we have too much product. So if you have too much product, it's going to shift toward the reactant side. Because Le Chatelier's principles, you got to go to where they ain't. Wherever the concentration is, tries to go to where they ain't. Okay? So goes to the left for the reactants. All right, now we can fill in the chart. Well, if we're going to the reactants, remember our reactant is COF2. So if it's going to our reactants, then is it? Is that wrong? Yes. Okay, cool. I wrote it right. Going to our reactants, we're getting more reactants and we're subtracting product. Okay. So if our new expression is 0.1 plus 2x, 0.2 minus x, 0.2 minus x. Okay. Now we run it back all over again. So our new expression should be, come on, work with me. Okay. So if our equilibrium constant is, I'm just going to use this for some more space. Kc equals 2.0. Q is only used to determine what direction it'll go. The moment you decide what direction it goes, throw Q out the window. You don't need Q, all right? Because if we're looking at our equilibrium concentrations, we only want to deal with K because K is relative to the equilibrium, all right? So when you're done with Q, just throw it out. You don't need it. Fuck Q. 0.2 minus X. 0.2 minus X. Because remember, this was our relative expression for CO2 and CF4 to the first power. 0.1 plus 2x to the second power. Well, looky here. It's exactly what we did before. All right. This is actually 0.2 minus x. Well, if you multiply them by the same, expression, this is a squared. If you guys remember math class in the FOIL shit, it's that exact same thing. Plus 2x also the second power equals 2. Let's just square root both sides. Let's get rid of those exponents. Square root of 2, we already know it's 1.41 equals 0.2 minus x over 0.1 plus 2x. Well, we have just one variable. No weird parentheses, no weird exponent. Let's just multiply it out like we normally did, like what we did before. Just algebra the shit out of it. Multiply that over. That's going to be 0.141 plus 2.82 x equals 0.2 minus x. Okay, so let's add our x right here, plus x, subtract 0.141. All right, that's going to be, let's use a different color. 3.82 x equals 0.0590. Now we just solve for x. Divide 3.82. Divide by 3.82. X equals 0.0154. All right. And for looking for our final concentrations, do not forget, plug in x. Because remember, your equilibrium constants were left as relative adding or subtracting your molar ratio. So make sure you plug in x. How close to done are we? Okay, we're pretty close. Okay, so for number 5, consider the reaction. We're going back to our hydrosulfuric acid. Okay, so for Kc is, again, that really small number, 1.7 times 10 to the negative 7. Okay, a half liter flask. Okay. All right. So if we're given our initial concentration, that's going to be in molarity, but we're given moles and liter. We just got to convert it. And in test 3, you'll be converting it. Actually, no, you'll be converting it. Yeah. The IS table uses molarity in moles. You can use molarity as well, but I think test 3 especially, you have to convert it to moles because those are titrations. It's a very long process, very long type of question, but the more you practice it, it's really easy. Maybe not what you want to hear from TA, but it's whatever. So our moles is given 0.0125 over our liters. That's going to be 0.500. Okay. Molarity is going to be 0.02. Whoops. 50 molarity. So that's our initial concentration of our reactant. We're not given any product. Well, we don't have to solve for Q because you got to go toward the product. not the product. Yeah, the product. There's no products. There's only one direction to go. We got to make some product. So we already know the signs. All right, we're going to make some. Okay. Plus 2x plus x minus 2x. Right? Our new expression is 0.025 minus 2x, and then just normal x. Okay. We already talked about this. In what direction? It's going to go forward. No product. So there's only one direction to go to make product. And our new expression, all right, our k constant expression will be h2 to the squared to the second power, s2, h2s2, all right? And that is 1.7 times 10 to the negative 7 equals 2x, 2x, 0.025 minus 2x, 2. All right. So let's just multiply that in. That's going to be, okay, that's the expression. Ooh, that's right. I forgot. If your KC is very small, because what you have right here, there's no way to get rid of that because mathematically it's just going to be a very long process. And even then, you can't really get rid of it because you're going to have to do the whole FOIL process you did in math class. You don't really like doing that. I hate doing that. I don't want to do that. What you can do is if your KC is very small, that means your ratio of product to reactant is extremely small. You barely have any product because for KC, just to visualize it for you, is 1.7 times 10 to the negative 7. Well, that's 0.256. That's how many moles of product you'll have per mole of reactant. Very small, extremely small. Okay. So it's pretty negligible because look at how many zeros there are. So a good check is, okay, let's take our concentration, 0.025, divide it by our K constant. And, oh, okay, it's 1.5 times 10 to the 5th. If it's greater than 400, ignore it. You don't even have to do that. Just cross this out. It's a lot easier. Don't cross out the numerator because you still want the ratio. It's going to be a very small ratio, but you still want the numerator. But for that denominator, don't worry about it. And the thing is, pay attention to that. You will do that again on the next test. For acids and bases, you're going to do that. It's going to be a lot of fun. You're going to love it. Okay. Now solve for the equilibrium. So if our new equilibrium expression is 2x, 2 to the x, all right. Well, if we multiply that out, there's going to be 2x to the third power. So multiply that x in, it's another x, okay? 0.025 minus 2x over 2. Well, don't forget, we got rid of that because the amount you subtract from the original concentration, very negligible. Okay. So we just leave it like that. Well, let's multiply this out a little bit. Pay attention to this because the biggest mistake I saw last semester is, even though I pointed out, you got to multiply to both. All right, both the exponent to the variable and to that coefficient. You keep it there. All right. Well, I think I missed that earlier because you got to do it over here first and then multiply it over because that's actually going to be 4x squared times x. So it's going to be 4x cubed. There we go. Make sure you multiply it out to both the coefficient and the x. Okay. So we multiply that out further. Let's multiply at the bottom. It's going to be 4x3 over 0.000625. It's 1.7 times 10 to the negative 7. Multiply that over. 4x3 equals 1.06 times 10 to the negative 10. All right. divide by 4, and then cube root it. Whole bunch of the math stuff, yada, yada, yada. I am pretty sure you guys can do that. Actually, no. Let's not have acid. I want to go too fast. Cube root it. Get rid of that cube. Cube root it. And now our x is only 3.0 times 10 negative 4 molarity. Okay. So if that's our x, that's not the last step. Because remember, the last step is plugging them in. So, well, this is just one. So you can write just 3.0 times 10 to the negative 4 molarity. But for here, you got to multiply by 2. So 2 times 3.0 times 10 to the negative 4. That's going to be 6.0 times 10 to the negative 4. Those are your final concentrations. I think that's it. All right. I'm going to stop the share now. I'm going to end the recording.